Very good. As we said just now, today we are going to learn a new technique, which is referred to it as a force method. So if in the exam you heard about force method that you need to analyze your structure through force method, we are referring to this technique. Inside the force method, we need to know the deflection of our structures. So before we go through the force method, we are going to learn how to calculate the deflection of a structure under external load that has been applied to it. I will introduce here two techniques, but the one that we are going to use uh, inside your force method is the first one that we refer to it as virtual work method. So virtual work method is the one that is going to be using the force method technique. And I have another technique which is used normally for simply supported structure. That technique is just for your self-study. Some of you may have learned some of these techniques before this in other subjects like strength of material or static, but we are going to go into details of this technique this time, and you will see how we can use them for calculation of deformation in trusses, in beams, and also in frames. So try to learn this part very well, because after this, basically these calculations are the main part of the force method. And you will see that basically if you don't learn this part well, you will have problem in order to apply the force method to your structure. My slide is a little bit small, so normally I zoom in so that you can see it better. Um, Unfortunately, I didn't have time before this to type them. It's all my handwriting. As I said, some part is going to be additional, and I will inform you that part that is just for your self-study. Okay, let's start with the virtual work method. As I said, this technique is going to be used to calculate the deflection of our structure. This is a general technique, can be applied to truss, can be applied to beam, can be applied for frames. So any type of a structure that you have, you can easily use this method in order to calculate its deflection. This technique was developed a long time ago. The concept is like this. Assume you have a structure that is shown here by the black color. So this can be a truss, can be a beam, can be a frame, anything. We didn't show any specific shape for it. It can be any type of a structure. And as you can see, we have applied two external forces, P1 and P2. These forces also can be in any location and can be in any direction. And then the structure has two supports at the base. And our intention here is to calculate how much is the deflection at point A at this location. And you can see that the deflection can be calculated in different directions. But here, our intention is to calculate it vertically. So we want to know if we apply P1 and P2 to this structure, how much point A is going to go down or go up under these loads. So in order to do this calculation, basically in the virtual work method, we are going to apply a force exactly to the location that we want to calculate the deflection, where in this case is going to be point A. So this force is going to be shown by F bar. F bar doesn't exist in reality, but we are going to apply it there. That's why we call it virtual work, meaning the work which is not real. So we apply F bar to that location, and exactly in the direction that we want to calculate the deflection. If you want to calculate deflection horizontally, you need to apply it horizontally. If you want to calculate vertically, you will apply it vertically. So F bar has been applied to point A, and now our interest is to calculate how much is this delta. Okay, in order to calculate that one, we are going to use this equation. This equation says if you multiply F bar, that virtual work, to the displacement that you are looking for, it equals to a small f bar. This is not P, this is a small f bar. Maybe it is F bar multiplied by delta L. So let's see what is this F bar and what is this delta L. Right now we know F bar, the big F bar here, is basically the virtual work that we apply to point A. And delta is basically the deflection that you want to calculate. There are two more parameters in the right side of this equation that we don't know. One of them is this F bar. This F bar are the force inside your structure when you apply the virtual force to point A. So they don't come from external forces. This internal force are going to be calculated based on the force, the virtual force that you apply to point A. So meaning you need to have one structure without those external forces. You apply F bar only to point A, and you see what is the internal force inside your structure for all members. Let's say you have a truss with 3 elements. So inside each element you're going to have one F bar, and those F bar need to be calculated and put inside our equation. And this delta L basically are the deflection or deformation inside your elements, this time due to the external forces. That means when you want to calculate this delta L, we don't have any more F bar, and we have only the real structure. So I will repeat again. Our intention is to calculate deflection at point A, and we are going to apply a virtual force that we call it F bar to point A. This F bar, if is multiplied by the delta that we are looking for, is going to equal to summation of internal forces due to this F bar multiplied by internal deflections due to the external forces. So you can see here we need to have two structures in order to calculate this delta. One structure is going to be the real one under the real force. From this structure, we are going to calculate the deflection inside our member. So delta L is going to be calculated due to the force that comes from external loads. Second structure is going to be another structure similar to the first one without the external forces, and we are going to apply only F bar. And due to that F bar, we are going to calculate how much is the internal forces, that we call it small F bar. If you multiply those small F bar to their deflection and you sum it up, it's going to equal to big F bar multiplied by delta. So you may say that, okay, how we can use this equation in order to calculate delta? One easy way to do this calculation is to assume that our F bar equals to 1, because this virtual force can be any value. If we assume that F bar is 1, so we can directly calculate our delta. So delta is going to equal to internal forces due to that single unit force that we apply to point A, multiplied by the deflection that comes from the real structure. So let's see what does it mean if we want to apply it to a truss structure, for example. Down here, you can see we have a truss, which is under 2-point loads of P. Let's assume that the internal force inside structural elements due to this P are named P1, P2, P3 until P10. Our intention is to calculate how much is delta at point A. So we apply this P to this truss, and we want to know how much is delta at point A. Due to this P, we are going to have some internal forces, P1 to P10. In order to calculate how much is delta according to this equation, we need to apply a unit force to point A and calculate how much is the internal forces due to that F. So we need to have another truss similar to the first one, but this time without the external forces. Only we are going to apply a unit force to point A. So we can calculate easily these internal forces from the techniques that we have learned before. So we call this one P bar or F bar. If you multiply this F bar to the deflection inside these elements due to these external forces and sum it up, you can get how much is this delta. But from the string of material, you know that inside the truss, if you know how much is the force, its deflection can be easily calculated from this equation. PL over AI is the deflection due to the axial forces. So the moment that you can calculate the internal force due to external forces. So these P are inside your hand. If you want to know how much is the deflection, you just need to multiply it to the length and the cross section and the E. So you know how much is this delta L. So delta L can be easily calculated just by analyzing your frame and calculating the internal forces and putting it inside this equation. In other words, I can replace delta L inside the truss with this equation. So if you put this one back there, you can see our equation is going to change to this one. F bar multiplied by delta equals to P bar I, which are the forces that comes from this structure, multiplied by Pi, Li, Ai, and Ei, which comes from this structure. And if we assume that F bar is 1, our delta can be easily calculated through this equation. So in this equation, you can see only two parameters are not clear. One is P bar and one is P. P bar is the internal forces due to this unit force that you have applied to point A. So you can easily analyze your frame, get the internal forces, and put it inside your equation. On the other side, Pi is the internal forces inside the frame, inside your truss, due to the external forces, not that unit load. Meaning in this structure, we are only looking into the real structure without that virtual force. So you need to analyze it, get the P, put it inside this equation and calculate that delta. So for each element, you know what is delta and multiple to the force that comes from the unit load. You know how much is this delta multiplied by its force. You know how much is this delta L multiplied by its force. And then sum it up, can give you the deflection at that point. So if let's say instead of point A, you wanted to calculate deflection at this point. In that case, you need to apply this force at this location. And again, get what is the internal forces and put it here. That is going to give you the delta. You will go through the truss later, and it is just to know how this equation is going to be extracted from the main equation that we have. For beams, this was for truss. So our equation is this one, the main equation. And for any type of a structure, basically we can use it to extract equations similar to the one that we did for truss. So for beam, the story is a little bit different because inside beam we don't have basically deformation similar to the truss. Axial force inside beams are very small. But on the other side, what we have is the rotation that occurs in the section due to the external forces. So in order to do the calculation based on virtual work method, we need to do the same. Meaning we need to have one structure under the external force. We need to analyze that. And then we need to have another structure. We are going to apply a virtual force to the location that we want to calculate the displacement and analyze that one. And after that, put it inside the main equation and get a new equation. So these are some explanation that how we can convert the previous equation that we had to beams. For beams, our equation is going to change to these equations. Meaning if you want to calculate deflection of a beam, you can see the left side is similar to what we had for the truss, but the right side, instead of P and P bar, we have M and M bar. So this M and M bar basically are the bending moment inside your structure due to the external force and due to the virtual force. We will see some examples, but the main thing here is that we need to know the form of these equations. In the exam, sometimes we provide the equation for you, but better to memorize it. So for beams, what you need to do is basically if you have a structure like this under the external force of P1 and P2, and if you are interested to calculate the delta, let's say under P1, so you need to analyze your structure under the external forces and get the M. Of course, this M is going to vary from left to right of the right side of your beam. Is not going to have a constant value, but what is important is that you need to know what is the bending moment of your beam under the external force. And right now, if you're interested to calculate how much is the deflection at location of P1, so you apply one force at that location. This force always equals to 1 for the sake of simplicity. And due to this force, you need to calculate how much is m bar. So we have, again, two structures. One structure gives us the bending moment due to the external force. One structure gives us the bending moment due to the virtual force, which equals to 1. So this F gives us m bar. And the moment that you know the m bar and you know the m, you can put it inside our equation up here and calculate how much is delta. As I said, f bar equals to 1. So you need to calculate this integral. This integral, as you can see, is from 0 to L, meaning all over the length of your beam. So m bar comes from this structure, m comes from this structure. You just multiply it to each other, calculate the integral, and after that, calculate delta. Some of you may not remember how to calculate integral. Better to go and review back the integral because it is part of our calculations after this. Of course, we don't go through the calculation of integral of complicated math like cosine, sine. No, it is only a single simple algebra like x power 2, x power 3, this kind of calculations, which is very easy to do. But if you don't remember, you can go back and review how we do the calculations based on the integral. Okay, so this equation, which needs m bar and m, is to calculate delta. We can rewrite the same equation to calculate rotations if you want. As I said, this part is not very common to be used for for the force method, but if sometimes you need it, the same equations that we had, instead of delta, you can put theta. So let's say you want to know how much is deflection or rotation inside in the middle of your beam. So you need to apply a unit, basically bending moment in that location instead of applying a unit load. So due to that unit, the basically moment, you can calculate the bending moment and you can call it m bar. And due to the external forces, you can calculate the bending moment and you can call it m. So again, you multiply m to m bar and calculate the integral. From there, you can get what is the rotation. For your information, the direction of these basically bar is not very important. Meaning, if you want to calculate the deflection, let's say at point P1, you may apply the force through up or downward or upward. At the end of the day, after your calculation was completed, you get a positive or negative delta. If it was positive, that means the same direction is the deflection direction. If you got negative, that means it is opposite to the direction of your force. So if you don't know, you should apply it toward up or down. Doesn't matter because at the end, after your calculation, delta gives you a positive or negative sign that shows that deflection is occurring along the force or in opposite direction. Okay, let me just make a summary of what I said. I said for beams, if you want to calculate the deflection, you need to have, again, two structures. One structure is the one that you want to basically the real structure that is given to you. You need to calculate the bending moment due to the external force. And you need to have a second structure that is going to be subjected only to a virtual force. And this virtual force also is going to be applied at the location that you want to calculate delta. So we apply F or F bar in that location, and normally this F bar, as I said, is 1. So you get the bending moment. Just make sure that always the second structure doesn't have any external force. So it is only the same structure, meaning same EI, same length, same support condition, but without the external force. You apply the F, which is the virtual force, to the location of interest. You get the bending moment, you call it m bar. You get the bending moment from the first structure, you call it m. You multiply it, and you can get delta. And if you are interested in theta, instead of single force, apply a unit rotational or bending moment in that location. Apply one unit bending moment, then you can calculate theta instead. You will see some examples. Okay, let's go to the next page. There is one example here to show you how we use this virtual work method to calculate deflections. Here we have a simply supported beam that has a cantilever bar. And our intention is to calculate the displacement at point A. So we have basically three segments, AB, BC, and CD. Why we divide this into three segments? The reason is that the bending moment is changing from AB to BC and from BC to CD. So if you want to calculate M and M bar, and you want to put it inside the integral, it is very important to know the bending moment for each section. And you cannot have one equation for the whole beam because the bending moment is changing. So that's why when you have a beam or a frame, if you want to calculate the deflection, you need to divide it into a small segment in which in each segment you have one specific equation for the bending moment. Okay, so right now our beam is under a force at point C, 5 ton, and we have 1.5 meter cantilever and 3 meter and 3 meter, meaning 6 meter total length of the span, and I and E have been given to us. So we want to see how we can calculate the deflection at point A. Okay, our equation is this one. This is the one that we know. And we see that we have a bar multiplied by delta A. This is the deflection at point A, equals to integral from 0 to L m bar m dx over AI. Okay, so we need to calculate m bar, we need to calculate m. EI is a constant value and have been given to us. So the only two parameters that we don't know is m bar and m. M bar, as we said, should be calculated based on the F bar. And m should be calculated based on this real force. So we need to have two structures, basically. One structure is this one, without any change. We need to get the bending moment for each span, and we name it M. The second structure is similar to the first one. We remove the external force. Instead, we apply a unit force to point A. So this structure is going to give us M bar. So you need two structures always. One is the real structure. Second one, the same structure, you remove the external force, but you apply a unit load to the location of interest. Let's go and see. This is these two structures that we talk about. As you can see, the first one is the structure that has this P, 5 ton force at point C. And then the second structure is the structure that has one unit load at point A. So this structure is going to give us M bar, and this structure is going to give us M. As you can see, the one that gives us M is exactly similar to the structure that given to us. And the one that gives us M bar is exactly similar to that. We have removed this force. Instead, we have applied 1 ton force to point A. Okay? So you know how to do the calculation for bending moment. The first step is to calculate the support reactions. This 5 ton has been applied to the middle of the span, so we have 2.5 and 2.5 at point B and D. And if you want to calculate the support reaction for the second structure, you just need to write down sigma m at point B equals to 0. You get this one. Sigma fy equals to 0. You get this one. So I have done this one. You can see the value on the screen. And now we need to calculate the bending moment. As I said, since the bending moment in each part of this beam is not similar to other parts, so we need to calculate it for each span separately. So first we start from A to B. If you want to calculate the bending moment for this beam, you can see there is no force. So from A to B, M equals to 0. This is what we have written here. However, for second structure, we have a unit force over there. And if you cut it from any section with a distance of x, you can easily see that m bar equals to minus x, because 1 multiplied by x equals to plus m bar equals to 0. From there, you get m bar equals to minus x. So this x is the distance from the left side of your cantilever, meaning if x equals to 1, you get negative 1. X equals to 1.5, you get negative 1.5. So this equation can give us the bending moment all over span AB. So we calculated for AB. Now we can go for second part, from B to C. From B to C, you can see for the first structure, you have only this support reaction. So you have 2.5 multiplied by X if you cut it from any place. So that's why you get 2.5X. But for the second structure, if you want to cut it from any place, you have two forces, one ton is here and 5/4. So it's going to be multiplication of these two to the distance, like the one that you can see in the right side. So don't forget that the X is going to start from the beginning of the second segment. So in each segment that you calculate, you need to start your X from that location. You see, for the first span, X starts from here. We go to the second span, X starts from here. And this is how we do the calculation. So if you calculate right now, the bending moment here is going to be 1 multiplied by this length and 5/4 multiplied by this length. And then you have the same bar over there, which gives you this bending. So we got the bending moment for the second span, and then we go to the last part. Okay, for the last part, either you can say you can cut it from here, and you have this 2.5 and this distance and this 5 ton, or it would be easy if you look to the right side of your beam and you cut it from the right side. So in that case, you are going to have 2.5 multiplied by that X. If you do this, meaning if you cut from the right side and you look into the right side, you should do it for both of the beams, both the structures. Meaning you cannot do one from this side and another one from this side. In the calculation of N and M bar, the origin of X should be similar. So if you want to calculate the bending moment, all from left to right, for the up and down should be the same. Or if suddenly you feel that from right side, the calculation is more easier, so you can move your origin from right side and say that 2.5 multiplied by this X is giving me the bending moment, and you put it here. From down here also 1/4 multiplied by this X, give me the bending moment, and you write it down here. The most important thing is that you cover all spans and you get the bending moment for all three spans that we have separately. The origin of X can vary, meaning, for example, for the second part, you could say that I want to do the calculation from the right side. If you want to do that for the bound down here, second structure, also you should do the same. Okay, so this is right now the part that we have got all these bending moments, and they are all based on X. And according to our equations, we need to multiply M to M bar and do the calculation of the integral. So let's go and do it. So here you can see we have three integrals from A to B, B to C, and C to D. So you just need to put the values there. M bar is minus X, but M equals to 0. So if you multiply these two, become 0. So the first part doesn't give us any deflection. And then we go to the second part. You need to multiply this one to this one, as you can see here. And B to C is from 0 to 3. Why 0? Because we are calculating span by span. Since the length of this span is 3 meters, so it starts from 0 to 3. And then you go to the third span from D to C or C to D, again from 0 to 3. So it's going to be 0 to 3, and then you put this M bar that you have calculated for this span, and this M that you calculated for this bar. So after that, you just need to do math. You just need to put the values inside and do the calculations, and finally you get 16.8 over EI. So you can see here we got a negative value for our delta A. So this negative value says to me that the direction of deflection is in opposite direction of this force. Meaning if you apply 5 ton here, the beam is going to go up rather than coming down because we got a negative value. So we have 1 centimeter displacement toward up under that load. So this is how you do the calculation in order to get the deflections of a beam. Let's go to the next slide. Here I have another example for you, but this time we have done calculations for rotation. So in this example, you can see we have a simply supported beam with a length of L, and we are interested to know how much is rotation at point B due to uniform load of W. So we want to calculate the rotation. So this is our equations, if you remember. We said we just replace delta with theta, and instead of applying a unit load to that location, we are applying a unit bending moment, m bar. So we have again two structures. One structure is giving us m, is exactly the same structure without any change. We need to calculate its bending moment to calculate this m. The second structure is going to be similar to the first one, but without the external load. Instead, we apply here rotational moment to point B because our intention is to calculate rotation at point B. And the intensity is going to be also a unit, meaning 1 ton force for 1 kilonewton meter. So we need to calculate the bending moment for this structure. We need to calculate the bending moment for the virtual structure and put it inside our equation and get rotation. So if you want to calculate the bending moment, it's very easy. You have to calculate the support reactions and then multiple support reaction to this force, and you can easily calculate the bending moment. So I have done this one here. So I cut the beam from there. So this M can be easily calculated from this origin. A support reaction multiplied by X, Wx multiple X over 2 gives us M. This is the M. And if you want to calculate the bending moment for the second structure, you have the support reaction 1 over L multiplied by X, it gives you M bar. So you put M and M bar inside the equation, and then from there you get how much is the theta. So if you do the calculations, you get theta P equals to this value, and it is positive. That means rotation is occurring exactly in the same angle or direction of this M bar. So this is the rotation of that location. So you see the calculation is similar to the calculation of deflection. The only difference is that instead of a unit load, we put here unit moment, and everything is going to be the same. To calculate the M, you need to calculate the M bar and put it inside our integral and get the theta. Okay, just this one is just for your self-understanding, and normally in the exam and final exam and the test, we don't ask you to go through this calculation. Here, what I wanted to transfer to you is that in frames, right now we saw how do you do the calculation for beams. In frames, you have columns, and inside columns, normally you have large axial forces, unlike beams that the axial force there is very small. So in the columns, if you want to calculate in a frame that has columns and beam, if you want to calculate deflection, you may include the effect of axial force together with bending moment. In that case, your calculation is going to be more accurate than the time that you only consider the bending moment inside your calculation. Just now we saw for the truss structure that have a large axial force inside them. Our equation is P bar L over AI. P bar is the internal force due to the virtual work, and P is the internal force due to the real force. For beams, we just saw that we have this equation, M bar over EI. And M was the bending moment due to the real force, and bar was the bending moment due to the virtual force. So if you want to consider the effect of both, you can sum it up, meaning you can calculate M and M bar, and you can calculate P and P bar for that frame, and then put it inside the equation and get the deflection. So this way you will have a more accurate delta. In many cases, we normally assume that this P over P bar over EI is very small value. So we only go through these calculations, and we neglect the effect of axial force in the deflection. So this is something that normally, as I said, we don't ask you to do inside the exam and inside your test. But in the reality, if you were working inside a consultant company and you wanted to calculate the deflection, and you knew that the column is carrying a large axial force, then you can include the effect of that deformation into your calculation by adding this equation to the equations that we had before. For rotation also, the story is exactly the same. So you just need to calculate M and N bar due to the real forces and the virtual moment that you have applied, together with P and P bar due to the real force and the virtual bending moment that you have applied to that specific location. And then you can get the theta. As I said, often we only assume that the first part is acting and is having the main effect, and the axial force doesn't have too much effect except for trusses. In the truss, only this part is the main part, and bending moment, as you know, is almost zero. So here I have put one example just for your self-study. You can go through this example if later you were studying at home. I briefly explained that what's happening, and then later the detail you can study at home. This is a frame, and we have a 60-ton force applied to point C. We have an internal hinge over there. So our frame is statically determinate because we have 4 support reactions and 1 hinge. This hinge is giving us 1 additional equation. So basically the number of unknown support reaction can decrease to 3. Our intention here is we want to calculate the rotation at point A, left side of point C, and we want to also consider the effect of axial deformation. So since we want to calculate the rotation, according to this equation, we need to apply bending moment at point C in the virtual structure. So we are going to have 2 structures. One structure is going to be this one. So you can see we have it here. And the second structure is going to be a virtual structure. We remove the external force and we apply unit bending moment to point C. Because we want to calculate rotation, we apply bending moment. And we are applying it to point C because we want to know how much is the rotation at point C. So we have 2 structures. For these 2 structures, we need to calculate M and P from this structure, M bar and P bar from this structure because they are virtual. So we need to divide this frame also into a smaller segment because P, P bar, and M bar are going to be different for each segment. So we can divide it into segment AB, BC, CD, and DE. And for each part, see how much is M, how much is P, and then put it inside this equation and get the rotation. So this is something that you see I have done it here for each basically, for each section from A to B, P, P bar, M, and bar have been calculated together with free body diagrams. And then from B to C, D to C, E to D, at home try to look at it. It's very easy, just cut and calculate the bending moment and axial forces. So right now that we have all those P, P bar, M, and M bar, you just need to put it inside this equation and calculate how much is the bending moment inside, how much is the rotation inside your frame. So we have done this calculation. What is very important to share with you here is that at the end, you get one value for the first part of the integral, which is due to the rotation due to the bending moment, and you get another value due to the axial force. So this part shows how much axial force is affecting the result of theta, and this part shows how much bending moment affecting the calculated theta. So if you see, we have got these 2 values, and if you compare them, you can see the effect of axial force is almost 100 times smaller than the bending moment. So this is why, as I said, in the calculation of theta and delta in the frame, normally we can assume that the effect of axial force is insignificant, and we can do only the calculations for bending moment and get the theta or delta based on the bending moments. The reason is that even if you do the calculation for P and P bar, meaning you consider the effect of axial force, it's not going to change the result too much. If I remove this one, I get 0.0079. If I include this one, I get 0.008. You see the difference is very, very small. It's not worthy to go through all these calculations and do this all integral to just have almost less than 1% difference. So this is just one example to show you how much is the importance of the effects of axial force inside frames. There are exceptional cases. You may need to do it and then change and then decide whether P is important or not. But as I said, in the truss, the M is not important, and we only focus on P and P bar. Okay, until now, what we learned was regarding the calculation of deflection using virtual work method. There is another technique that you may have learned about it before this, that we call it elastic load method. It is applied only to simply supported beams. And in this technique, basically, what we need to do is that, let's say this beam is given to you, and they ask you to calculate the deflection and rotation in the midspan, for example. So what you need to do is to get the bending moment of this beam. This is the bending moment diagram. And then divide this bending moment diagram to EI. E is the modulus of elasticity, and I is the moment of inertia. So the moment that you got this one, you can cut it from the location of interest, which is here, point A. If you calculate the bending moment at point A, it's going to give you the displacement and due to the Q. And if you calculate the shear force, it's going to give you the rotation due to the uniform load. So you see, the procedure is very easy. You don't need to do any calculation of integral. There is one example in the right side for you. We have a P applied to a simply supported beam. So we got the bending moment diagram, and then we divide this bending moment diagram to EI, and then we cut it from here, and we get how much is the bending moment at point A, how much is the shear force, and this is going to give us the deflection and also gives us the displacement. If you are interested, again, you can read this one at home, but we don't use this one in the force method because this is mostly applied to simply supported techniques. And it was just for your review, if you were interested. Okay, so with this introduction that I gave to you, now we can proceed with the force method, which is the main target of our today's class, to see how we can use a new technique rather than using previous two techniques that we have learned. As I said, we have learned moment distribution and slope deflection method so far. And today we are going to use force method to analyze our frames. Okay, so before I start the force method, if any of you have any question regarding the calculation of delta and theta through virtual work method, you can ask. Otherwise, we can continue with the force method.